unfortunate situation that we'll know more soon. Let me end there.
Thank you very much. So I'm sure there are lots of questions.
So what are the possible reasons why 270 gigahertz changes the data?
So the 217 gigahertz data, it's not 100% certain. Well, it's not certain what's going on. My best interpretation is that there's correlated noise in the 217 gigahertz data. So what Planck does in their analysis is they have many detectors on the experiment. They treat each detector as if it makes an independent map of the sky. And they cross-correlate those maps. Those detectors are observing the sky at the same time. They're sitting in the same cooler. Remember that whole cooler's vibrating. It didn't meet spec. So we know that's one thing that's not working the way it's supposed to work. We had similar issues on WMAP. The mirror surface didn't meet spec. We had to correct for it. The 217 detectors seem to be more vulnerable to this vibration, and that's producing correlated noise. Intriguingly, if you just throw away the first month of Planck data from 217, you get the same answer we do. If you cross-correlate 217 from different seasons, you get the same answer we do. All the difference comes from the first month of 217 gigahertz data. So I think there was some vibrational problems in that early data that was producing correlated noise. So I think that's the problem there.
Is there any way to know what was wrong during the first month of data?
Yes, there's all kinds of housekeeping data on the experiment. I think as all the Planck, one of the things that will be clear with 5 seasons of data, you can do everything in close correlation. Just throw out that first year and see if it's all driven by that. And that'll be interesting to see. Another worry I have on the Planck data is one of the unpleasant surprises for the Planck team was when the satellite got out to L2, it was at a solar minimum. And this happened to be the quietest solar minimum we've had in recorded history. It may have been probably quieter than the Wonder minimum last 100 years. When the sun is quiet, that means the solar wind is weaker. That means more galactic cosmic rays get in. These low-energy galactic cosmic rays interacted with the Planck detectors. And the interactions were worse than they thought it would be because the cosmic rays hit the material in the satellite, created secondaries. The secondaries bombarded the bolometers. There's really high amplitude noise in the Planck data. And they had to go in, devise an algorithm that removed cosmic ray hits by hand. One of the heroes of the Planck experiment, unsung heroes of the Planck experiment, and it's unsung because actually on the outside don't know who's the key people responsible, were the people who devised the algorithms for removing the cosmic rays. Without that work, the Planck data would be useless, and they were able to make those corrections. Well, the unsung heroes, I would be much more comfortable if there was an end-to-end simulation of the Planck data. This is what we've done with WMAP and what we do with ACT. You run the data through your pipeline, simulation data through your pipeline, and show that you recover in an end-to-end simulation what you get back. Some of the referees of the Planck papers might have even encouraged them to do this stronger. But you only have so much leverage as a referee.
did not comment on the implications of Planck data onto the contending inflation models. And that was to some of us, many of us, that was one other highlight that if one must, contrast somewhat to the W map. And after the recalibration, do you happen to know if there's any migration?
Yes, so what happens is the values of NS that they were showing at the Paris meeting were 0.968 something, pretty close to this, 0.97. So their values for, it's not clear what the NS value is. What was said in the Bologna meeting, which really confuses me, is they ran two different likelihood codes on the existing data, and they have values that differ between 0.965 and 0.97. And I can't understand how the same data run through two different codes differ by that. It's less than a sigma, and they say it's 0.7 sigma. That's data. So I'm confused by this. Why basically the Cambridge code and the Paris code get different results. And this was only stated, I saw on video the talk, and there's a difference. So I'd like to understand that better. So that's one of the things I'd like to read more closely. The Planck limit on R is not much better than WMAP. WMAP had a limit of R less than 0.12, and Planck had a limit of R less than 0.11. Okay. My colleague Paul Steinhardt wrote this paper about how this now changes the way we think about inflation. I said, Paul, the value hasn't changed. He said, yeah, but it's Planck. We want to hang our thing on something new. What's going to be very interesting, so, the bicep experiment, I think it's turned out that dust has played a bigger role than people thought. We probably don't have a protection there. There'll be a bicep cross-Planck analysis. I anticipate that may give us our best constraint on R. And we'll see where that ends up. There's when I learned about inflation, simplest models were lambda 5/4 and m²/5². And you can either say, well, those are toy models, or say, look, we just see a little bit of the inflaton potential. It's very reasonable that's a good approximation. With the WMAP data, we had already ruled out lambda 5/4. And with Planck, m²/5² is, with the 2013 data, it's kind of disfavored about it.
That was what I was asking.
And our reanalysis makes it a little less disfavored, but it's not, whether it's 2 sigma off or 1.8 sigma off, you just want better data. And this is something where, given all those upcoming experiments, probably within a year, within 2015, and certainly by 2016. Either m²/5² is going to be ruled out, at more than 3 sigma. These ground-based and balloon-based experiments are going to improve our limits on R. Or we'll have a detection. So, we're really, for these simplest inflationary models, in a very interesting time. And what that means in terms of inflationary model building is we can distinguish, broadly. I have a piece of chalk I put in my pocket. I'll take some more. I may end up stealing by the end of this day 1 or 2 pieces of your chalk. But there's a whole box of it. Right? You can distinguish between models that look like this, sort of m²/5², and models that look more like this, where you've got a flatter potential. Now, there are intermediate models, right? Because we're always looking at effective field theory. So, there are things, there are models, either Silverstein or collaborators have models where the effective theory looks like more like 5 to 2/3. And that gives you a lower value of R.
Also, Stravinsky's are squares now.
Right, so-
in the center.
Yeah, so, the first model, as you said, that people
I know,
wrote down
ironically.
was Stravinsky's model, right? And Stravinsky's model, which has a non-minimally coupled field coupled to gravity, fits the data beautifully. And, one of the things that's, if this next generation of experiments achieves their goals, and there are two big challenges, I think, for doing that. One is, this is really hard experiments. They have to control their systematics well enough. And the other is we have to understand the galaxy model, which is going to be another challenge to model the dust, model the silicon. Then they should get to the range of detecting it for Stravinsky's inflation models. And I think with multiple frequencies, and I feel I'm very pleased we're living in an epoch where we have multiple approaches to doing these experiments and lots of different competing teams. Because I suspect most of the approaches will work, but some will work better than others. And that we'll be able to get to this issue.
Any questions from students?
So one of the recently popular models of dark matter is self-interacting dark matter. So I'm wondering whether that kind of model will influence any parameters in those surveys.
Not really. I mean, they're interesting. I mean, having written some of the papers on that, I think it's very interesting. But I think about it just to go back to this plot. This shows the amplitude of fluctuation versus scale. And these are the scales here that we measure with microwave background temperature fluctuations. So I mentioned with polarization, you get another factor 2 or so in scale. You get to about there in terms of mass scale, around 10 to 15 solar. When we talk about self-interacting dark matter, the dark matter properties become important on these scales. And they have big effects on dwarf galaxies, where you're looking at masses of 10 to the 9 solar masses. So they're, potentially very interesting. This was a talk with the theme of the success of the Standard Model. If I was giving a talk on big issues, one of the ones that I think is most interesting is whether or not the dark matter models, when we go to simulate galaxies, fit their observed properties. And I think they do pretty well on the scale of clusters or groups or big galaxies. When we get down to dwarf galaxies, things get interesting. Now the challenge is with dwarf galaxies is galaxy formation feedback, and outflows, all that complex physics plays an important role. And I think it's clear that there's a deviation between simulation and observation. And people then go in and tweak the simulation. And what we don't know is whether that's showing the limitations of our simulation or the need for new physics. And self-interacting dark matter is one example of new physics. It's an interesting one to think about because it has zero effect on this picture. And it just shows up here. And similar to that are these warm dark matter models. The scale at which the dark matter streams in those models is down here. So you don't see it in this agreement. And it affects things like dwarfs. I think the challenge for looking at this is figuring out ways in which we could look at how the dark matter is distributed. Most of our observations tell us about where the stars are, not where the dark matter is. And we need to figure out where the dark matter is. There are a bunch of ways of getting at that. One is things like strong lensing. That's been telling us what's going on in clusters. We'd like to get to even smaller scales, and there's millilensing that gets at that. Another way of getting at this is looking at things like dynamics of tidal tails of dwarf galaxies and watching the material that streams out of this. one of the things that I've had a lot of fun thinking about with W-First, this is this project that Yan-Ting mentioned I've been involved with, is ways in which we can use precision measurements of astrometry, getting accurate positions of stars on the sky to figure out about the dark matter. When I was a graduate student, I thought astrometry was the most boring possible thing in astronomy, getting such accurate positions. Now as I think about what do I want to do as I get older and we'll have all this W-First data, and by the time it launches and finishes, I'm into my 60s or 70s, right? Probably astrometry. And you know, and a lot of it's motivated by thinking about ways in which we can get at the dark matter properties, ways in which we can probe these scales here to look at things like self-interacting dark matter.
Any final questions? Or you can ask the questions after the talk. So as advertised, next Wednesday, David will give a talk on his take on bicep 2 and inflation. So please come over to ASIAA. And so let's thank David.